Okay guys, so this question is from Kepler's Laws worksheet and it's question number 2. And it reads, a satellite with an orbital period of exactly 24 hours is always positioned over the same spot on the Earth. This is known as geosynchronous orbit. Television, communication, and weather satellites all use geosynchronous orbits. At what distance would a satellite have to orbit the Earth in order to have a geosynchronous orbit if the mass of the Earth is 5.97 times 10 to the power of 24 kilograms and the radius of the Earth is 6.38 times 10 to the 6? So first of all, let's figure out what is it that we're trying to find in this question. Okay, so this is our Earth, and then up above the Earth, we've got a satellite orbiting the Earth. What we're trying to find in terms of the formula is we're trying to find the radius of the satellite's orbital period or orbital path, which comes from the center of the Earth all the way to the center of the radius. Now, really, that's not what we're trying to find, which is why we've been given this radius over here, because actually what we're trying to find is the distance from the Earth's surface to the satellite's center, or to the satellite. So we're trying to find this D value, which is slightly less than the R value and includes this radius of the Earth that we've already been given. So essentially what we need to find through our calculations is we need to find the total radius of the orbital path. Then we need to subtract the radius of the Earth, and that's going to give us the distance. So we're just trying to find the radius so that we can take away the Earth's radius and give us the distance that the satellite is orbiting above the Earth. So I'm going to rewrite that as we are trying to find D. And to find D, we're going to find R, and then we're going to subtract the radius of the Earth, which is 6.38 times 10 to the power of 6 meters. Okay, so we are trying to figure out what is R in order to do that. So we need to figure out what variables do we have here that can give us R. So the first variable that we have is in the first sentence. We know that the satellite's orbital period is 24 hours. So T in this particular scenario is 24 hours. However, hours is not the correct unit for time. So the first thing we're going to need to do is multiply that by 3,600 seconds in an hour to give us a total orbital period of 86,400 seconds. Okay, then we can move on. The next two sentences are just fluff. They don't contain any information in them. Same really with the next sentence, which is just asking or telling you what variable you're trying to find. Okay, but we do have mass in this case. Okay, when it asks for mass in these two particular formulas, they're not asking for the mass of the satellite or the mass of the orbiting object. When we're using these last two formulas for Kepler's law, the mass that they're talking about is the mass of the object being orbited, right? Because essentially this is just a smaller version of finding the force of gravity. We're going to multiply the gravitational constant by the mass. So we need to know the mass of the object that's being orbited, then multiply by its gravitational constant, and that's going to give us essentially the force that that mass is exerting on the orbiting object, which is of course going to influence its speed and its acceleration. So the mass we're looking for here is the mass of the Earth, because the mass of the Earth is what's being orbited. Okay, and then we also have our universal gravitational constant, which is G, which is 6.673 times 10 to the power of negative 11. And then the units are really complicated. You don't actually even need to write them down. So I'm just going to leave them blank. Actually, I'll put them in. So it's Newton meter squared divided by kilogram squared. Okay, so now we should have enough variables in order to solve this equation. So if we look here, we've got time, we've got mass, we've got gravity and radius. So we need to find a variable or a formula that includes all of those variables. The equation for orbital period does include all of those variables. This is going to be annoying to write. Okay. Give me one moment. radius cubed times or divided by gm. Okay, so that was our formula for orbital period. We have the time. We have the gravitational universal constant. We've got the mass of the object that we're orbiting, so we should be able to rearrange this formula in order to solve for r. Okay, so the first thing that I'm going to move over is that 2 pi. So we're multiplying that entire thing by 2 pi. So I'm going to divide both sides by 2 pi in order to get rid of it. Okay, so then I end up with that entire thing is being equal to the square root of the radius cubed divided by gm. So the next thing I'm going to do is get rid of the square root sign by squaring t divided by 2 pi. It's pretty important to remember kind of the order that you do these things in, because when it comes to calculating r, you want to remember that this is the only thing you're squaring. So you're going to take the orbital period, divide it by 2 pi, and then you're going to square that number. You're not going to square the entire kind of formula that we get over here, just that small section that was moved over before you square. Okay, so then the next thing that we're going to do is we want to get rid of this gm. It's being divided on the other side, so we are going to multiply this by gm. So again, you're not going to go g times m times t divided by 2 pi and then square that entire thing. Just the part in the brackets is getting squared before you then multiply that answer by g times m. And then the last thing we do is we've got to the power of 3 over here. So on the other side, we're going to do the same thing, but it's going to be a 3 cubed root. Okay, so essentially what we're going to do is we're going to take the orbital period, which is t. Okay, we're going to divide t by 2 pi. Then we're going to square that number. Okay, then that number that we get, we're going to multiply by the mass. We're going to multiply by the gravitational constant. Then we're going to take that entire number, which is here, and we're going to cube root it, which will give us the radius. So you should have ended up with a radius of essentially 42,233,240.1 meters, okay, which means that large distance that we talked about, or that large radius, is that number. Okay, then we're going to take that number there and we are going to subtract the Earth's radius, which we've written up here. Copy that formula. Okay, and we're going to end up with a slightly smaller distance of 35,853,240.1 meters is the distance that the satellite needs to orbit above the Earth's surface in order to have that speed and that orbital period. Okay, hopefully that makes sense. The only trick to this question, or these formulas in general, is knowing that the mass that you're looking for is always the mass of the object that is being orbited, not the mass of the satellite in this case. And then that was a kind of tricky formula to manipulate. Just make sure that you do things in the correct order. For example, you're not square rooting g times m in this particular equation, just t divided by 2 pi.